Now there was a question about the change of the chemistry during an event. I will try to explain that again, maybe with a schematic sketch. I try to put some more light here. No. No. Not sure how I can. No. No. Go down. Yeah, but then that doesn't help with reading, huh? You shouldn't sleep here. How can I switch it? Maybe the video producer can change the light to get. If you have a hill slope with groundwater like this, then you have heavy rainfall. Yeah? This is the hydrograph. So it's discharge R in, for instance, cubic meters per second. And it's a low flow situation till here. Yeah? Now the heavy rainfall comes. Some of the rainfall falls to the ground, does not infiltrate, generates overland flow, and goes to the river. Other goes down to the groundwater table. What does the groundwater table do? It increases. So the groundwater table maybe is now like this. So you have an increase of the groundwater table. What does that increase of the groundwater table do? It increases the groundwater discharge into this river. Yeah? Overall, we observe low flow, heavy rainfall comes. We see an increase of the hydrograph, a peak, and maybe a falling limb. We have a flood event like this. Now the question is, how much water follows the green pathway on the surface into the river, and how much water goes to the down to the groundwater and enters the groundwater like this. Yeah. To separate these two dominant flow pathways, of course, reality is much more complex, and you have all sorts of interactions. But to separate this, you can look at the chemistry. During this part, the chemistry, for instance, the chloride concentration is up here. Yeah. Now I put a second axis. This is the chloride concentration. I put it in a bracket to say it's a concentration, Cl minus. And maybe during the event, the chloride concentration goes down and goes up again. This decrease of the chloride concentration here, so this movement, is a lot of overland flow, rainfall, surface runoff, that comes with little chloride going into that river. Yeah? Therefore, it goes down. After the peak or during the peak, maybe now more groundwater comes in, so water going down, and pushes out the groundwater. This rise of the groundwater table causes an increased groundwater discharge to that river. This groundwater has much more chloride. Now you have an increase of chloride again. And this kind of behavior of the chloride helps us to separate this overland flow from the groundwater flow. Yeah? We do the same with environmental isotopes or with other chemical parameters. Is it a bit clear? Good. Of course, in reality, you don't have only one overland flow and one groundwater flow. That would be nicer. It's much more complex, and a full catchment has urban areas, forested areas, and it's much more complex, but we keep that for later. Yeah? I want you to get a conceptual understanding of the method. Yes, please. Yes. No. You cannot generalize this. No, but you have to measure that, and these kind of studies have been done hundreds of times in this literature. And then through the many studies, you get an understanding. And interesting is that in most of the catchment, you show quite an important role of groundwater. While most hydraulic engineers always think a flood is done by overland flow, surface runoff, yeah, we can show with isotopes in chemistry that most of the flood volume actually comes from groundwater or a subsurface flow. Yeah. It's usually underestimated. We do more details in other courses. For this introduction, this is getting a bit too far. But generally, the importance of here what is called old water discharge or groundwater discharge is very, very high, usually underestimated. Good. Now I go to hydrograph analysis a little bit. Here you see another hydrograph with two separations. The one is called, we have here point A. Oh, what did I push? Oh, sorry, what did I do? Video protector. Yeah, I see it here as well, but I'm afraid that the beamer is off. Excuse me. Reset? No. Sorry. All right. Sorry, Rob. Rob? I think now it's restarting. Maybe the lamp got too hot or something. I don't know. Now we hear the ventilator again, so it's coming. Ah, good. Oh, one slide. Hydrograph analysis. Here, this is the flood hydrograph with a peak flow here, rising limb, falling limb, or recession curve. Yeah, and here people were separating it in two components, so-called direct runoff, also called surface runoff, and base flow. Base flow, they mean by groundwater discharge. Now we have a funny behavior. Here, everything during low flow, everything is base flow, everything is groundwater. Then heavy rain starts, direct runoff becomes important, rising limb, more direct runoff. You even have negative base flow. How can that be? And then base flow comes up again, and at this time, overland flow or direct runoff is gone, and it's basically 100% base flow again. How can that be? That can be explained with storage of overland flow in the groundwater next to the channel. Yeah? You have here a water level rise, then you have a flow reverse, not from the groundwater to the river, so this is this direction. Now you have from the river to the groundwater, so exfiltrating conditions that the river is storing floodwater in the banks of the alluvium. So this is then this storage of water which causes here a negative base flow, bank storage. Yeah. Then the water table is going down again, and you see a flow back to the river, and even an increased base flow than before, because now the more recharge has happened in the banks here, and you have more discharge to the main river. Huh? So here's a separation into base flow and direct runoff, causing through bank storage even negative base flow for a short time. And this negative base flow is the temporary storage of water in the banks. Another more classical hydrograph separation is just to draw a line from A to B. Yeah? If you plot this at log scale, semi-log scale, then you often see here a significant change in the gradient. We look at that in a few figures from now. And people don't just ignore these processes and just draw a line. This is, if you're just interested in how much volume of water here, this volume here, how much that is and how much you need to store that in a flood retention basin, for instance, then it's okay to draw just this line, yeah, this AB line, and just say, oh, well, this is the amount of water that we need to store. This A to B line, if you have it now, we have here a log scale on the left-hand side, and then usually you have a very significant change of that point when the base flow is dominating again with a change in the gradient. This is less steep than this one. Yeah. Then you can do that A to B line. You can describe this depletion curve or recession curve with an exponential function, and calculate this direct runoff. And again, this volume might be very important if you do flood estimation and flood retention, and you need to store so many cubic meters of water somewhere in the landscape or in a reservoir or somewhere. Another thing I want to mention in relation to flood, but I know you do more detailed hydraulics with my colleagues. We have a flood curve, which is the curve A. Then we have a translation from the peak here to a situation B, which is further downstream. And you're not only having a shift of that peak, you also have an attenuation. So that means a lowering of the flood peak. So here you have a steeper, sharper peak, while here you have a wider, broader peak. The volume below the area A and B should be the same, but it's just a retention of the curve. Where does that come from? If you have two rivers, actually one river and at two observation stations, one is upstream, B is downstream, why do we have that change in the form of the hydrograph? Due to some dispersion of that wave, through some flooding, dispersion processes, that the further downstream you are, the more dispersion you have, and then a smearing out of the flood peak, you can call it like this. And the attenuation is then the lowering of the peak. Now we measure it, flood peak in two stations in, I've forgotten where I got this figure from, sorry for this. But here you have also another interesting phenomenon. Now the upstream station, the blue line, has an earlier peak, lower peak, and now the downstream station has a higher peak and also much higher volume of discharge. So the area under the curve is much larger, and that's, you can explain how. That also from the side, some rivers coming in and contributing to the overall discharge. So the further downstream station, the black one, is much larger catchment and also receives further inputs. Generally, we have to differentiate with rivers with affluent conditions. This is usually the low flow situation, that the groundwater is contributing to the stream flow. Groundwater is discharging and providing groundwater flow. While affluent conditions, that's the other side, that the river is actually exfiltrating to the groundwater, discharging to the groundwater. You have influent conditions from the river, from the groundwater point of view, flowing into the groundwater. And doing this bank storage, we have a change from affluent to influent, temporary influent conditions, and back again. That you can have a change of reverse flow lines as we had in the previous figure. Usually most of the rivers are either gaining or losing. Now this would be a gaining river and this would be a losing river. Losing in terms of losing water to the groundwater. Gaining means gaining discharge from the groundwater. I skipped that briefly. Maybe the flow duration curve is another important figure which I should explain and which you should know from this lecture. Here we sort all the discharge what we have. Not, for instance, you have 1 year. Usually you have up and down because of change of discharge. Now you sort them by the volume, and you have here a percentage of exceedance. Yeah? Here is 0 and there is 100%. If you sort them, here we have a log scale, if it looks a bit like this, then you have, this is the highest discharge measured in your period, for instance 1 year or 10 years or whatever you have, and this is the lowest. Yeah? And you sort them by the discharge volume. Huh? And then you always have a curve like this, and this is the so-called flow duration curve. Huh? So you destroy the continuation of the flow. In the hydrograph, we just sort the time series based on discharge. Now you see here two different flow duration curves of the same catchment. One is the present condition. That's a somewhat thinner black line. It's the lower line. And the thicker black line is the one above here. That's the virgin condition. That means that the river in its virgin stage would have a flow duration curve like this. How can you explain that? That the complete natural conditions looks different than the present situation. And again, during the high flows, you hardly see any difference, at least at this scale. They look the same. But during mean flow and low flow, you see quite significant change between natural and virgin condition. What do you think could be the reason for that? Somebody said? Transfer of water, yeah. Then, in particular, during low flow, some water is stolen from this river and pumped somewhere else, or maybe just abstraction for agriculture. Yeah, this is, I think, the case here, that some water is abstracted for irrigation. You don't see that during the high flow because this is maybe only 1-2 cubic meters per second. And for the whole river, 1-2 cubic meters per second, you don't see the high flows, even if it happened during the high flow. But during the low flows, you see that quite significantly, that the abstraction is quite sensitive. Yeah, that's what you see here. This is a workshop. I skipped that. Good. Now I go to the last estimation method for discharge, and that's so-called effective precipitation and runoff coefficient. I think I mentioned runoff coefficient before. The runoff coefficient is the effective precipitation, so that part of the rainfall that is not sitting in the interception storage or in any other DSDT, but is contributing to discharge, yeah, divided by the total precipitation. Yeah. Could be, if you separate the effective precipitation with this line like here, you call this one the effective precipitation or the direct runoff, QS here. You divide this by the total precipitation and then you come to this number. For instance, could be, say, 30%. That means 30% of the total rainfall makes it during this event also to the discharge. Yeah, that's a percentage. That characterizes your basin. So what is the difference? If you have a basin that has a runoff coefficient of 50% and the one that has 10%. What's the difference in the basin? One has 10% runoff coefficient, the other one has 50% runoff coefficient. What would be the difference? Yeah, the one is producing always half of the rainfall makes it to the runoff. The other one, only 10% on average. So it's storing much more water, much more DSTT, much more holding back of the water. Yeah. Which one is steeper? What do you think? The 50% or the 10% runoff coefficient catchment? The 50%, yes. It's much more responsive, steeper slopes, fast runoff. Or maybe has urban areas with a lot of urbanized roads and buildings and so where water can be discharging directly. Yeah. There are many ways suggested in the literature to calculate this PE, that's effective precipitation. I will just show you a few of them. One is the so-called index method. The index method or the phi index method, there you subtract always a constant part of the rainfall, for instance, in this case 2 millimeters per hour. Yeah? You subtract it from the rainfall hydrograph. And everything above 2 millimeters per hour, this gray shaded area, that is the direct runoff. So you say every hour 2 millimeters are infiltrating into the ground and don't do anything to runoff generation, yeah, or hold back in the vegetation. But the rest above these 2 millimeters per hour, this is discharge which is exceeding a threshold and then contributing to discharge directly. Yes? It's related to infiltration capacity, yes. Yeah, absolutely. Yeah. For engineering hydrology, sometimes you need some quick and dirty methods. You don't have always measurements there where you would like to have them for many years. And so you have to work with some simple empirical equations to estimate the peak flow. Why could be a peak flow estimation very important? Why do we need this? For instance, design a bridge, design a overflow of a reservoir, or these type of things, drainage system. Therefore, the oldest method, and many others since then, are based on the rational method, but it's already 160 years old. This is a very simple peak flow estimation technique where you have a runoff coefficient, which you can look up in tables like this. Then you have an I parameter and a TC parameter, which is the runoff concentration time. I is the rainfall. Where's I? Difficult. Here. The constant rate rainfall from the intensity duration frequency curve. You read this out of your IDF curve, and then you multiply by area. Yeah. Yeah, it's a very quick and dirty method, but it's amazing how much this method or some further developments of this method, which are just a little bit better but not much better, are still used in practice. In many of you maybe on the road design and so from your previous job, and you know that these type of empirical formulas are still used a lot. I know that in Ethiopia it's used a lot, but in many other countries as well. And it's easy to criticize, but on the other hand, it's very difficult to do something much better because you have no data, so you have to come up with something simple that works. And there's a lot of experience with this, so often it's not so bad, I need to say, but it's of course a very simple approach. Another important formula is the time of concentration, so how quickly the runoff can make it to the outflow. That's described with the so-called Kirchhoff formula, yeah, where L is the maximum length of the catchment and S is the slope of the catchment over the distance L. Let's say something how steep your catchment is, and then you have a Kirchhoff formula in hours that helps you to estimate how quickly the runoff makes it to your catchment outlet. Another method is the time area method. Instead of going to the equation, I explain it here on this figure. The rainfall intensity can be described like this. Every time step, for instance, 1 hour, you have a variable rainfall amount. This is a Hieto graph. Every hour we have so much rainfall. This rainfall is then producing some overland flow. We said effective rainfall is not producing runoff. Not overland flow is a special thing. Producing runoff. You can also delineate your catchment in areas which have the same runoff response time. That means the same amount of time needed to flow from this point to the outlet. Yeah? That's so-called isochrones. These are lines with the same runoff concentration time. So the amount of time, for instance, 6 hours, is needed on is needed from here to get to the outlet. And you can draw these isochrone lines throughout your catchment. If this is, for instance, the 3-hour line and this is the 4-hour line, that means everything between here needs on average 3.5 hours to keep it simple. 3.5 hours to contribute to the discharge. Now you have your rainfall event in hourly time steps, for instance, and then this first rainfall event in the first hour, only the rainfall falling to this area also makes it to the outlet because it takes 1 hour or half an hour to get there. During the next time step, next delta T, this rainfall falling to this area makes it to the outlet, but also from this area, the A2 area, the rainfall from the previous hour now also arrives here. So you route the water per time step, always one time step down. Yeah? Rainfall from here, next time step is there, next time step there, then there, then there, then there, and there. And that adds up to a hydrograph like this. Yeah? The formula are described here. Look at them in detail. Everybody can quickly program something like this in Excel, for instance. And it's a very simple rainfall runoff model, very simple hydrograph model, just to produce a hydrograph. Time area method is called. Good. Let me conclude this chapter. I explained about rating curves. They are valid over a certain range of water levels. They help us to make out of water levels discharge. They need to be updated regularly because of sediment transport, because of changes in the cross sections, etc. There are also many different types of gauging stations. We looked at quite a number of different pictures, and I think you will go to somewhat more in detail in the hydraulics lectures. I want you to know the different catchment response types, and now at the second bullet point, and use the right terminology. So if you talk about a seasonal river or ephemeral river or a perennial river, you should know what that is and what that means. That's always important for communicating about science. We talked about hydrograph separations. So hydrograph separations I tried to explain here down there. When we try to separate the hydrograph in different components, could be direct runoff and base flow, could be overland flow and groundwater flow. We discussed that a little bit, and much more of this will come in the following lectures. Yeah. But we discussed in particular the one in runoff dynamics. So very fast runoff, usually it's overland flow, but also more delayed runoff, which is usually groundwater flow. We looked at interpretation of the depletion curve, not so much. We looked at the flow duration curve just before. This is the, if we ordered all the discharge according to magnitude, to flow volume, then we have a curve with a characteristic shape, which helps us to interpret the catchment response behavior of a catchment. Yeah. Maybe with the flow duration curve, maybe one more example. Forgotten to mention that, but flow duration curves is something all of you will have to work in the future somehow, at some stage, you know. And fully, maybe you draw some yourself and discuss it with a friend. What do they mean? If the flow duration curve is the discharge R, for instance, in cubic meters per second, versus time, this is 100%. This would be 0% exceedance, and then it looks, for instance, like this. Yeah, these are the high flows. They are only exceeded. If this is 10%, in 10% of the time, the discharge is higher than this. Usually, actually, should draw it more neatly. Usually, looks like this. Yeah. So you have a few very high peaks and something like this. Yeah. What is the difference between this curve and the flow duration curve that look like this? The orange one is much flatter, has much lower peaks, but higher base flow, higher low flow. Yeah. Another flow duration curve might look like the blue line. So in 10% of the time you have discharge, can be very high for a short time, but in 90% of the time or 85% of the time it's basically nothing. With the blue curve, what would you expect such a curve? In which climate zone or which kind of catchment would you expect the blue curve? Yeah, the flow duration curve of the blue shape. Where would you expect that? An arid catchment, for instance, yeah. And the orange, which is maybe the opposite, in a humid, temperate, humid catchment, very boring catchment where not much dynamics. Huh? It can be not really high, but also not really low. Very, very kind of always very average runoff behavior. Maybe there's a big reservoir which filters out a lot of this variability. Yeah? And the white one is something in between. Yeah. Is that clear? Good. If you understand this, this is very good. Because all of you will have to interpret the shape of these type of curves later. Flow duration curves. Yeah, we looked at the. We didn't do hydrograph separation. We also looked at effective precipitation with the phi index method. It's a constant loss rate. That means it always subtracts, for instance, 2 millimeters per hour. For instance, not always 2 millimeters per hour, depending on the catchment, which is a constant subtraction from the rainfall intensity. We also talked about some simple black box methods, estimate hydrograph peaks. I mean, with black box method, I mean very simple method with very little physical basis, like the rational method, which helps you to, in a quick and dirty way, to estimate the peak flow. Finally, my last point in this lecture is that there is a direct link between the runoff dynamics and the hydrochemistry. Yeah, this link exists. I tried to explain it with the overland flow discharge. Here with the green and the orange, and that these can have different chemistry of the water, and that's very important to separate the overland flow, green curve, with the subsurface flow components. Yeah, that's a very important thing. If you understand this already, then I'm very pleased. Good. It was, a very quick run through a lot of material on runoff. Of course, much more needs to be said, For us hydrologists, the runoff is a key parameter. Yeah, many other modules will follow where we will discuss hydrograph in much more detail. But in this early stage, are there any questions from your side? Yes, please. Which one? The flow duration curve? Yeah. The blue curve, in less than 10%, in about 10% of the time, you really have high discharge, huh? If this is 20%, in more than 20% of the time, so this is 80% of the time, is always zero, no runoff. But then, between 10 and 20% of the time, discharge is in this area, but in less than 10 is even higher. So you have a few days with very high discharge in this catchment. That's typical for arid catchment. The orange is the opposite. It's always very average. You have the high flows don't go really that high. The low flows certainly don't reach zero. They're always kind of stable. 50% of the time, if this is 50% of the time, discharge is always the same. Yeah, this is really extreme. So there's no real low flow in this catchment. It's always average flow. Yeah, very boring catchment, you could argue. Could be that there's a very big reservoir and everything is very regulated. Huh? That all the high flow pulses and the low flow pulses are completely filtered out. If you have big reservoirs, you could do something like this. Yeah. And the white one is something in between, with having high flows, but not as high as the blue one, but having low flows, which are also going lower than this very average catchment. The flow duration curve, these are all three different types of flow duration curves. They describe the catchment response behavior. Huh? We ordered here the days according to the magnitude of the discharge, and then we always have a falling curve from the left to the right. Yeah. And the shape of that curve tells us a lot about the hydrology of the catchment. Tells us something about the climatic area, tells us something about the steepness of the catchment, how big or small it is. Yeah. Maybe the orange one is a huge catchment, very big, very average behavior, while the blue one is a very small one where you have a very spiky response. Very small catchments can react very extreme. Yeah. Can it tell us something about the geology, can us something about the land use, etc. So the flow duration curve is summarizing a lot of the characteristics that are within a catchment summarized in one curve. Therefore, I like this curve. Yeah. But it's nothing else than the hydrograph. The hydrograph, again, discharge versus time. So R in, let's say, millimeters per days, for instance, can look like this in your catchment. This is time in days. Yeah. But for the flow duration curve, you take this hydrograph and you just sort it by the magnitude of the discharge. Huh? These are the highest peaks, and then the low flows. Other questions? No more questions. It was a long day, huh? Yes, please. It's the last lecture for me. That's true. But you will have many, many more. Okay, it's you are in the module 2. It's called Hydrology and Hydraulics. It's a combined exam from hydrology and hydraulics. Usually we have the first hour. Don't nail me down on this 60 minutes. Usually first hour or first half, could also be 90 minutes, is hydrology, or hydraulics, doesn't matter. And the other half is the other subject. There's a break in between. We want you to first, for instance, do the hydrology part of the exam, 60 minutes. You get some questions, you answer the questions, all right. You do handwriting, not like my handwriting, you know. Nice that we can read it properly, you know. So if you cannot read it, then it's very difficult to give good marks. You know? So please, I'm not very good in this, but try to write in such a way that we can read it properly. Maybe we also ask you to make a short sketch or a drawing or some computations. Please bring a calculator with you. All the details you will get an email, and that will all explain that. And then there's a break, 15 minutes. You can go to the restroom or drink a coffee or whatever doping you need. And then there's the other exam. Yeah. Usually hydraulics is very much on computation, on calculating things, and hydrology is a mixture between calculating things but also interpreting a flow duration curve or calculating lysimeter equation and so. Dr. De Laat usually also gives usually it's one afternoon or one Saturday morning or one evening, depending on your other lectures. I know it's very busy for you at the moment. So we have to find a time where you are available. Also exam training, when he stands then here and shows exams from the last years and shows the computations to demonstrate what kind of questions are there. Yeah. So come to that. That's useful. Yeah. Otherwise, look at my lectures. For me, it's most important that you understand. Of course, you need to do some calculations. We are an engineering, water science and engineering program, so you must be able to make some simple computations. But most important is that you understand why a flow duration curve looks like this, yeah? Why the rainfall error is so large, and you know, these kind of things. But I try to discuss with you also. Yeah. And then this counts a certain percentage. It's on Moodle. I think it's 40% or 50%. The exam, and the other 50% are the assignments. Dr. De Laat is doing the assignments with you. You have to hand them in, usually at the end of the day. And then he gives you marks for that as well, and then we average that. And then I think it's 50-50. And then you usually pass. I know hydraulics is extremely full because of all these exercises also. Then you have remote sensing where you have to do assignments. I know it's very busy. Module 3 and so is then a little bit less busy on your schedule. But you keep on working very hard. I think that will remain. Good. Other questions? Yes? Last question. Yes, please. This arrow is the rainfall falling to this hill slope. Some of the water is transferred by overland flow to the river. That's the green arrow. Some of the water infiltrates, going to the groundwater, and as groundwater discharging to the river. Both have different chemistry. To separate how much overland flow versus how much groundwater flow enters to that river, we can do by measuring the chemistry of that river. And then we can separate. Oh, my figure is then here. This is the flood hydrograph going up and down. This is the chloride concentration, for instance, being stable, then going down because of more overland flow, and then going up again because of more groundwater flow again. Usually the overland flow is the much faster responding system than the groundwater flow. But depends on the specific situation in your catchment. Good. So I won't see you in this setting again. I wish you good luck with further studying. It was a pleasure to be here, give a couple of lectures. You know that I'm teaching very little because of my other responsibilities, but I always enjoy to do some lecturing at least. I wish you a lot of success, and I might meet some of you then again in other courses or in the master exams or wherever. Success. Thank you very much.